All right, welcome back. We're still in section 3 from topic 4. Now that we understand ionization energy, let's look at a few examples of it. So example 7 says, the first and second ionization energies of magnesium are both relatively low, but the third ionization energy requirement jumps to 5 times the previous level. Explain this. And what is the most likely ion for magnesium to become when it is ionized? So this is a great question. I really like this question because it really is testing whether or not you understand what ionization energy is. So let's think about magnesium in terms of its electronic structure. So I'm going to draw that out here. So we have magnesium, and magnesium is in row 3, which indicates that it has 3 energy levels. Now, if I were to write out the configuration for magnesium to kind of figure out where all the electrons go, let's do that real quick. It doesn't take too long. 1s2, 2s2, 2p6, and then 3s2. So what that indicates is that in the first energy level, we have 2 electrons. So I'll just draw 2 electrons there. In the second energy level total, we have 2 plus 6, so that's 8. And then in the third energy level, we have 2 electrons. So the problem states that removing the first and second electrons, that's the first and second ionization energies, they're relatively low. But when you go to remove the third electron, which is the third ionization energy, apparently the requirement for energy jumps significantly. Hopefully by drawing the picture you can see why that is. The first 2 electrons are in the outermost energy level. While they take energy to remove, it's not going to take a lot because they're pretty far from the nucleus. There's a lot of shielding going on in the middle. But once you remove the first and second electron, and now you go to remove a third electron, you're now removing a third electron from the second energy level. The second energy level is a lot closer to the nucleus, less shielding, and therefore electrons here are going to be held a lot tighter, which means it's going to take a lot more energy to remove. So based on knowing that, based on understanding that the first and second ionization energies will happen fairly easily, what is the most likely ion for magnesium to become when it's ionized? Considering that the first 2 electrons were relatively easy to remove, it's likely that magnesium would become positive 2. And think about that. That actually lines up with what we know, because where is magnesium on the periodic table? It's in the alkaline earth group, which is group 2. And group 2 elements form positive 2 charges. Let's look at example 8. Which of the following elements is expected to have the higher ionization energy? Let's find out where these elements are on the periodic table and see if we can use the trend. So I see sodium and magnesium are right next to each other. Aluminum's a little further down, so all 3 of these are so far in the same period. Potassium is in a group lower, it's in row 4, and then calcium is in the same. So if I think about the trend of ionization energy, where ionization energy increases as you go up a group and over to the right, I can first get rid of potassium and calcium as candidates because they're going to be lower. They have 4 energy levels, whereas these 3 elements only have 3. When I compare sodium, magnesium, and aluminum, because they're in the same period, I know the one that's going to be larger will be towards the right, which, if I compare those, aluminum is further to the right. Therefore, aluminum is expected to have the higher ionization energy. And below, what concept does the following chemical equation represent? I see that I started out with a neutral atom, and I've somehow created a positive ion because I lost an electron. That is the definition of ionization energy. More specifically, I could even say this represents the first ionization energy because it was neutral and it lost its first electron. All right, the last trend is electron affinity. Now, by definition, this trend is the opposite of ionization energy. Let's read the definition together. Electron affinity is defined as the energy released when an atom in the gas phase accepts an electron. So where ionization energy required energy, this is energy released. And why? Because we are accepting an electron, not getting rid of one. So we are creating an anion, which is a negative ion. You can think of it as this is the element's affinity to want to accept electrons to itself, rather than get rid of one. So the definition is opposite, but if we think about the trend is actually the same as ionization energy. It will increase as we go up a group. That's the same as saying decreases down a group. And it will increase across a period. Now, there's an exception. With electron affinity, the first three elements in the noble gases are actually excluded from the trend. Specifically, helium, neon, and argon. We would not count these elements in the group trend. Why? Because these elements, being noble gases, and because of their atomic and electronic structure, they don't want to accept electrons. They do not have a high affinity for doing so. So we remove them from the trend. And so if we were to think about that, based on the trend and knowing that these three elements are removed, what element then would have the highest electron affinity? Or in other words, which element is the most probable to want to accept an electron? Fluorine, because it's the furthest up a group and over to the right. How do we show this in a chemical reaction? We can show that by doing this. Take a neutral element, but add the electron on the reactant side. As a result of accepting that electron, look what gets created, an anion. And energy is released. That's why energy is written as a product, because it's released from that process. Here's the trend again. Once again, notice that it is a trend. There are going to be exceptions. For example, as I move across a period, going from, let's say, sodium all the way to chlorine, it does generally increase, but there's a little variation in there, and that's okay. That concludes this video as well as topic 4. We'll see you in topic 5.